Good morning and welcome back. Today we will talk about our last chapter, chapter 14. But before we start, I think many students care about our midterm exam, our quiz number 2. So let me take a brief, let me show you quiz number 2. Okay, I just make a new announcement. The quiz number 2 will be an open book and take-home exam. It covers chapters 10 and 11, the last two chapters, and the total score will be 100, 10%. I will post the questions on ILMS here, on ILMS, and you have to upload your answers in PDF format, in PDF to ILMS. It's due 14 p.m. Tuesday. So next Tuesday, next week, that homework will not be considered for grading. Keep this in mind. Okay, that's it. Just give you a chance to study something in more detail. Okay, so today I will talk about radiation by moving charges. Okay, talk about radiations by moving charges. We will talk about linear Chap potential, starting from the retarded green functions, and we will calculate from the potential. The linear Chap potential is a very famous potential because their forms looks easy. Therefore, it's much easier to remember. However, the electric and magnetic field derived from linear Chap potential is not that straightforward. Okay, so that part we will omit and skip because it's quite advanced. You can study by yourself. However, we will focus on the phenomena of the single moving charge, radiation by a point charge. Okay, so let's review the basic equations. Unfortunately, Jackson switched to Gaussian unit systems from page 11, and therefore I will show you the SI equations, not Gaussian unit, but SI equations here in red, SI. So this is inhomogeneous wave equation with source. Inhomogeneous wave equation, but it's in a free space. So we don't have to worry about epsilon and mu. They are just equals epsilon 0, mu 0. Inhomogeneous because of this one, because this one. For Gaussian unit, it's minus 4 pi rho. We have a 4 pi. However, for SI unit, we have rho over epsilon 0. For Gaussian unit, we have 4 pi over C coefficient. For SI unit, we have mu 0 J. So we can rewrite into inhomogeneous wave equations. From this inhomogeneous wave equation, we found retarded Green's functions. Green's functions looks like this one. Okay. In fact, we talk about this retarded green function in chapter 8. And chapter 8, let me see, chapter 8. Just a moment. Sorry, not chapter 8, but chapter 6. Chapter 6, we talk about the retarded green functions with outgoing wave boundary conditions. Actually, if you may have a look at chapter 9, page 10, page 10 and page 9, you will find the retarded green functions. In chapter 9, page 10, okay? Chapter 9, page 10, you will find the retarded green functions. So we learned this one before. The retarded green function was derived from these equations. It's a little bit hot. Let me turn on the fan. Just a moment. Okay, so we learned this one in chapter 6. These equations in chapter 6 and as well as in chapter 9. Now we are going to use the retarded green function. And this time we have only one charge. Okay, we can simplify the equation a lot. Okay, charge distribution and current distribution will be easy because one charge. Okay, we need both phi and A to specify E and B unless the source has homogeneous time dependence. In chapters 9 and 10, the source has homogeneous time dependence, so we need phi or A, not both. But here, we consider a point charge. So it's not homogeneous time dependent. Exponential minus I omega t. Phi and A are not correlated. Therefore, we need both of them. Okay, that's our midterm exam questions. A qualitative picture of radiation by an accelerated charge. Initially, that's from Asberg, Fundamentals of Modern Physics. E field lines surrounding a stationary charge. Now, the charge moves constantly, or the charge accelerates. What will happen? The field line will change. A fraction of E field lines showing the effect of charge acceleration. Let me show you in more detail. Okay, so now let's have a look at linear Weichardt potentials and the derived fields for a point charge. What is linear Weichardt potential? Linear Weichardt potentials for a point charge is here. And we consider a point charge E that carry a sign E, might be plus, might be minus, moving along the orbit. So in terms of source coordinate, x prime, t prime, jx prime, t prime, and the orbit is in terms of the source coordinate t prime at the velocity v. Here, for example, the charged particle E and its orbit is here. Not circle, but arbitrary orbit. Arbitrary orbit. That's orbit of E. At time t prime, it sends a signal and take time to propagate to here. That's the point of observer, the point of observation. We have an observer here. So we measure at this point x t, a x t. This is observer's coordinates. Okay? From the origin is here. From here to observer is x. From here to here is x prime. But x prime is along these coordinates. Okay? How much time for the wave to propagate from here to here? Separation is r t prime. That means at t prime, the separation is r. That is x minus r, right? X minus r, and take the absolute value divided by the speed of light. It's free space, so the propagation time from here to here is r over c. Therefore, if an event occur at t prime here, it takes about t prime plus r over c to reach here. That's why this equation looks like here. Okay, so rho xt can be read into this one, charge times delta function. Charge density, that's charge density. EV delta, that's current density. So we can express in this form. Only when x prime equals r t prime, we got value. Otherwise, just zero. So we just evaluate at a specific time point t prime. Evaluate at t prime. So by substituting this equation to here, this equation to here, and this equation to here, we got these two equations. Okay, it's a volume integration plus time integrations. So volume integration is easy, relatively easy. This is volume integration. This is time integration. Volume integration tells us one thing. Only when x prime equals rt prime. So we can change this integration 1 over c e times, here, rho e. So we got e here. And delta function, these terms, give us 1. So eventually we have x minus x prime. S prime is occur at r, so becomes r absolute value x minus r t prime. Okay, replace this one with this one. Therefore, this one is also replaced with this one. And we can rewrite this equation into t prime plus r over c minus t here. Likewise, the vector potential can be read into this form. E dt prime beta. Why? Why beta? Here. V over c. V over c is defined as beta. Beta is a normalized with respect to the speed of light. Particle cannot exceed the speed of light. So v of the charged particle is always less than c. So it from 0 to 1 at most. How about this one? Okay. So linear V-charge potential looks simple. What happened to this one? Can we simplify this equation? Yes, we can do that. Just rewrite these equations again. We can rewrite this part into e dt prime, and we express a function f of t prime is as t prime plus r t prime over c. So it can rewrite into this form. Just rewrite this equation into this form. And what's next? Next one, we can use these properties. Gx delta fx minus a dx. We can gx is evaluated at when f of xi equals a. That is evaluate at this point. So we have the derivative absolute value, sum all the derivative, but in fact we have only one value. That is only 1 point. For 1 point charge, we have only 1 point. That is this one equals t. Okay, so in fact we can sum over all the possibilities, but in this case our possibility is limited to 1, just 1 point. So we can r t prime time derivative of this one, what will happen to be derived. E the same, E the same, beta the same, R the same, R the same. That's extra term here. It's evaluate at the retarded time. Evaluate at a time t prime equals t minus r t prime over c. It's retarded time. I don't like this term retarded time because it will be easily confused, but it's still better than the advanced time. That means the time that an event happened and take time to propagate to a later time, it propagate to another an observer. For example, I clap my hand at 10 o'clock, and you will receive the signal in roughly about, if we separate 3 meters, you will receive roughly the signal in 10 milliseconds. Okay, so 10 o'clock plus 10 milliseconds, and the signal is emitted at 10 o'clock because it needs to travel. That's not the speed of light, that's the speed of the sound. Speed of sound, just roughly 340 meters per second, much slower. For example, an event, a signal emitted from our moon, it takes about 1 second to reach the Earth. Okay, so a signal emitted at t prime, observer will receive a later time. That's why it's retarded time. Okay, it's not finished yet. What's this one? This one looks easy because looks like this one and derivative of this one. Okay, actually is the x minus r t prime over dt prime. We can write into this form: s prime minus 2x dot r plus r squared, the square root of this one. And square root of this one takes about t prime, and then move 1 over 2 to here, and we have minus 2x dt prime r plus 2r dt prime r t prime. Okay, and 2, 2, 2 cancel. So eventually we have a minus sign here, and this is r, and what else? And r time derivative give us the velocity. Okay, give us the velocity here, and x minus r here. x r x minus r means the signal directions. We can write into separation r, the length, and the direction. Uh, uh, so it's a normalized directions. Just indicate the directions. So let me show you these figures again. A particle, a charged particle, charge E, and move along this orbit. At time t prime, it send a signal, emit a signal, and take times to reach this observer. And the particle will then move to here at time t prime. At time t prime, the particle move to here, but the signal reach this point, the point of observation. And at this point, the tangential direction is the velocity, and x minus r and norm divided by r is the direction of the propagation signal emitted from here to here. Okay, so the f of t prime give us 1 minus beta dot n. Beta is always less than 1. N is the absolute value is 1. So the result is always less than 1. So this one is always greater than 0. Kappa is always greater than 0. We can define this one as kappa already done by substituting equation 5 into equation 3. Equation 3. So we have this equation: 5xt e 1 minus beta dot n over r, evaluate at the retarded time. Okay, A, vector potential, scalar potential, vector potential, E beta 1 minus beta dot n, evaluate over r, evaluate at the retarded time. Since this equation is quite simple, so we give it a name: linear Weichardt potentials. Linear Weichardt potentials. Let's check the dimension. 1 minus beta dot n normalized dimensionless. So this term is dimensionless. So scalar potential just E over R. Yeah. just the scalar potential's dimension. How about the vector potential? Vector potential is E over R, the same. Dimension is E over R. So for the Gaussian unit, phi and A are the same dimension. Phi and A are in the same dimensions. Not surprised. Okay. So keep this in mind. Many professors preferred ask you to write the linear Chap potential. Why? Because easy. You can write this equation easily. Okay, let's why. Move on. Okay, we have the potential. We have everything. We have the potential, linear Chap potential. What's next? Next one is to obtain E field and B field. And it will more convenient to use equation 1, not equation 14.8. Equation 14.8 looks very beautiful, concise, simple. However, equation 1 is more convenient. It's more convenient to use equation 1. Okay. So we will start from here. It's more convenient to use equation 1. Let's equation 1. So, okay. Optional. Okay. Now, let's start to calculate E field and B field. Okay. How to do that? First, we will introduce a function fr. It's a function of r. Gradient x fr you can write into this one and this one in terms of take the total derivative of f, because f just function of r. You can take the total derivative and then gradient xr. And gradient xr, we can use these properties. These properties we learned in chapter 1. Chapter 1, if you don't remember, just open your lecture notes. Study the course material again. In this one, the result will be simple. Just n at nt prime dfdr. Okay. So electric field equals minus gradient phi minus 1 over c partial a partial t. Okay. And all we need to do just perform the integration and be careful, use these properties. Gradient phi, okay? You can work on this one. Wow. And substituting this one, we got another one. This one is still the same to be evaluated. That's gradient phi. Phi is function of r, remember? R. So we can change the notation. We take the derivative of r, and we have a minus sign, and we have this one. And then we take the derivative of this one. We got another one. Okay, it's not finished yet. But I will stop here because in the next 4 slides, I consider it as optional because most of the students cannot remember the detailed derivations. Only 5%, maybe at the most 10%, has sufficient time to study this material. And those students are very smart. They can understand by themselves. All I need to do is provide the material and you can study by yourself. Okay, how to derive. If you don't understand, maybe you can go back to Griffiths. Griffiths detail how to derive this equation step by step. Okay, so I will skip this one. That's an advanced material. And just show you, B can be derived from curl of A, the same process. O from here. You can derive from E, N cross E, O derived from curl of A, the same. We have the same result. I will focus on here. After, just consider it as a box. Put the linear withdrawal potential inside, into the box, and we will have electric field and magnetic field. And magnetic field are related to electric field. So we can focus on one fields. For example, in this case, let's focus on electric field. Electric field can be divided into two terms. And they all evaluate at the retarded time. The electric field comes from two parts. One is velocity field, because it depends on many things, but mainly depends on the velocity beta. And second, we have acceleration field. Acceleration field depends on here. Okay? Let's check the dimension. N dimension is beta normalized velocity, so its dimension is gamma dimension is. So it's just equals to E over R squared and evaluate the retarded time. So the velocity field is proportional to 1 over R squared. Yes, the traditional format for electrostatic. However, we have another term here. Once again, let's check the dimension. E, N dimension is. We have beta time derivative. Beta dot equals d beta dt. Okay, d beta dt. C is the speed of light. 1 over c equals dt over dx. That's the speed of light. So dt cancel with this one. So it's beta over separations. So these two are the same dimension. So that's okay. But c is the speed of light and it's a constant. C is a constant speed of light. And beta is the normalized acceleration. So acceleration fields is proportional to beta dot over r. and is perpendicular to n. N is the direction of propagation from the source to the observer. N, once again, N is from here to here. And that means we emit a signal. Then the signal electric field will be perpendicular to these directions. Maybe in this direction, or this direction, but perpendicular to this one. Okay, that's good news. If we have acceleration in this direction, and then observer here will observe a E field perpendicular to N, and this one proportional to 1 over R squared. This one proportional to 1 over R. So we can expect acceleration field will become very important. And magnetic field can be derived from N cross E. So the discussions, we have 5 discussions. The velocity fields are essentially static field falling off as 1 over R squared. That's similar to the static fields. And for the acceleration fields, 13 and 14 acceleration fields shows that E and B and N are mutually orthogonal. E, B, N mutually orthogonal, normalized to each other as a typical of radiation fields. At far fields, yes, normalized. So just like E cross B equals X, there's pointing vectors, E cross H. So N is the direction of propagation. It will be normalized to mutually orthogonal to electric field and magnetic field. Okay. Note, we have 2 notes. The unit vector N points from the retarded position here and to here, observer. T and T prime are quantities in the same reference frame. Okay, here to here. More discussions. Discussion number 3. E and B in general have a broad frequency spectrum. It's not sinusoidal time dependent. It's a single point charge. Therefore, it corresponds very broad frequency spectrums, very broad, which applies to a non-dispersive medium. Okay, in this case, the vacuum, non-dispersive medium, from here to here, no material inside, it's vacuum. Signal at frequency travel at all frequencies travel at the speed c. E and B and T depend only on the instantaneous motion of the particle charge, of the point charge at a single retarded position. If the signal is propagate within a medium, it probably is dispersive, and different frequency will propagate at different velocity. In that case, the signal will distort. The signal emitted from here will be changed. The shape will be changed. Okay, but here is a simple case, simplified case. Okay. Discussion number 4. Quantity in the brackets are to be evaluated at the retarded time. Bracket are to be evaluated at the retarded time. which means evaluate at t prime. And t prime has simple relations. X is the position of the observer. T prime is evaluate at t prime, which means its position is here. And you can simply consider the separation from x minus r is here. X minus r is here, divided by r. Okay. And, sorry, this one separation divided by the speed of light. It takes times from t prime to t. When the orbit rt prime is a specified function of t prime, thus t prime depends on x and t. This makes the final expression for E a function of x and t. Okay, that means later on we will find some relations x and t. T prime can be expressed as x and t. Rewrite these equations. No other. C is a constant. Okay, for the same reason, the unit vector n here, unit vector n can be expressed as function of x and t. Okay, so everything can be expressed as x and t. Although we say evaluate at the retarded time, but it still can be found from x and t. Okay, they are correlated. Discussion number 5. The relations between the observer's time and the retarded time is here. Simple. T prime is the retarded time. T is the observer's time. Indicate that the signal from the charge travels at the speed c toward the observer, independent of the motion of the charge. That means if the charge moves toward you or away from you, they still travel at the speed of light, a constant speed of light. That's the universal speed of light, Einstein's second postulate. Okay. With the help of the computer, we can visualize very high speed, the image at very high speed. For example, if we have an array, a crystal, a particle at rest, you will see that's normal view at rest. If particle travel at the 0.5 speed of light, the rod appears straight. It's still straight, but what happened? If the particle moves much faster, it changes shape. Okay, change shape. If particle move at the speed of light, very, very close to the speed of light, for example, 0.99, then the lattice appears severely distorted. If particle travel at the speed c, everything will move to the front. Okay, so at rest, we have a small hole. We have a large opening. As we increase the speed, the opening will small and small and small. Looks like very small. Let's computer simulations. Let's the illustration of time retardation and the length contraction and time retardations. Computer can generate the graphics, shows the visual appearance of a three-dimensional lattice of rod and balls. That's the balls. That's the rod. Moving toward you at velocity at various speed. Let's obtain from Benson University Physics. Okay, that's very interesting because you might expect everything should be the same, no distortion, but in fact, they are not. They will change shape. They will change shape. They will change the appearance when the speed is very high. Okay, I will stop here. I will stop here, and uh, you can start to prepare your quiz number 2, and maybe you are ready. You are ready. So you are ready about quiz number 2. Okay. We still have 4 or 5 lessons. We can finish chapter 14 in time. So our final exam will be held at a classroom, at our old classroom, exactly the same classroom. Okay, and it will be open lecture note only. Open lecture note only. You cannot use your cell phone. You cannot use any other things. You cannot discuss with your friend, with your classmates. Okay, I will stop here. If you have any question, you are welcome to call on me without reservation during the office hour. That is every Thursdays and Tuesdays, 1 to 3 p.m. Okay, at my office, Physics Building, room 417. Okay, see you next time. Bye bye.